So this is ELC 131, Circuit Analysis 1. And we continue with this discussion, this video, talking about resistance. Now, in the last video, we started our discussion on resistance, but today we'll want to dig a little deeper and talk about some topics that we just didn't get to in the last video. So we talk about resistances. We can break these resistances into two broad general categories: ohmic resistances and non-ohmic resistances. Now, ohmic resistances are fixed resistors. As we talked about in the last presentation, our fixed resistors are components that are designed to oppose current. And we see a pictorial diagram of a fixed resistor, and the schematic symbols, both the US schematic symbol and the European schematic symbol for fixed resistors. Now, our non-ohmic resistances are resistances that change due to a change in a physical parameter. And two physical parameters we'll talk about today are temperature and light. So one of the components that exhibits a change in resistance as a function or due to a change in temperature is a thermistor. And we see the US schematic symbol for a thermistor and again the European schematic symbol. Now, thermistors can be either positive temperature coefficient thermistors, meaning the resistance increases as temperature increases, or they can be negative temperature coefficient thermistors, meaning the resistance decays or declines as temperature increases. The NTC is probably more widely used than the PTC, but in your schematic symbol, you will always have an algebraic sign here denoting whether the change in temperature, change in resistance is a positive or negative slope. Now, another non-ohmic resistance that you may encounter is the photoresistor. This is also referred to as a light-dependent resistor. And the schematic symbol in the US schematic symbol for the photoresistor and the European schematic symbol for the photoresistor. Now, let's take a look at these and see what they look like. And the thermistor, this is just one example, is just a small bead that is actually semiconductor material that has a change in resistance as a change in temperature. Thermistors can be much, much smaller than this, and they can also be much larger than this. This is just one example we have here in the lab. The light-dependent resistor is shown here. And you may have seen a light-dependent resistor if you have a lamp post in front of your house that turns on in the evening and turns off in the morning. That's the component that's used to sense the amount of light that's striking, or the light that's ambient, to turn the light off in the daytime and turn the light on in the nighttime. Now, the negative temperature coefficient thermistor has this response as a function of temperature. So we graph out temperature T on the x-axis. It's the independent variable. And we plot R, resistance, on the y-axis. It's the dependent variable. And this thermistor has essentially an e to the negative x, or a 1 over x response. Now, when we discuss and describe and quantify the operation of a thermistor, we talk about its resistance, R sub O, at the temperature T sub O, where T sub O is 25 degrees Celsius. And the resistance of the thermistor is just some value depending upon the construction of the thermistor at this particular temperature. The one we're going to look at today has a resistance of 10 k ohms at 25 degrees Celsius. Now, there's an equation that describes this function, the change in resistance as a change in temperature, and that equation is that RT, the resistance at some temperature T, equals R sub O times E to the beta, let me change my brackets here, E to the beta times 1 over T minus 1 over T sub O power. And of course is just a number, kind of like pi. E equals 2.781828 or something like that. E just describes how things change in nature. Now, in this equation, beta is the material constant, and that is given in Kelvin, or expressed in Kelvin. And the device that we're going to look at in the lab today has a beta value of 3,445 Kelvin. And in this equation, of course, temperature has to be expressed in kelvins so that all our units cancel in the exponent. Now, let's take a look at the change in resistance of this device. And we see that the thermistor is hooked up to an ohm meter, and here at room temperature, which is about 27 degrees Celsius, we've got 10.7 kiloohms. And I'll hold this between my fingers and heat it up, and we can see the resistance decreases as the temperature of the thermistor increases. Now, if I can cool this thermistor down, and I'll do that by putting a cool bottle of water on it, we should see the resistance fall or go above the 10.7 k. Then you can see we've increased to about 11 k. So the thermistor is widely used in a branch of electronics called instrumentation so that we can make electrical measurements of temperature. Now, the light-dependent resistor or photoresistor actually has a very similar response to the thermistor. The difference is, of course, we're looking at resistance as a function of light intensity, and the light intensity can be expressed in milliwatts per square centimeter of aperture or surface area. It can also be expressed in candelas, and it can also be expressed in lumens, depending upon which unit you want to use for light intensity. So we can see that the photoresistor is used as a variable resistance. The resistance changes, of course, as a function of light intensity. So let's take a look at the operation of this device. So we connected the light-dependent or photoresistor to the ohm meter, and we see that with room light striking it, we have about 1.5 kiloohms. And as I cover up the device and less light strikes it, Notice the resistance is getting larger and larger and larger as less light strikes the surface. So our photoresistor can be used to provide a change in resistance that is not directly proportional to, but is proportional to the change in light intensity. So another example of a non-ohmic resistance is the case of tungsten. And tungsten is the metal that's used for the filament of an incandescent lamp. Now, recall from our previous video that resistance R equals rho times length divided by cross-sectional area. And every material has some inherent value of resistivity. However, with tungsten, the value of resistivity changes as temperature changes. The resistivity of tungsten, rho, equals 6.05 times 10 to the negative 8 ohm meters times T raised to the 1.203 power. And the temperature T is expressed in Kelvin. So this would be the resistivity of tungsten at 0 degrees Kelvin. And as temperature increases, of course, the resistivity of the material increases. So we would have to substitute this rho at some temperature for the rho here, given the length and cross-sectional area, to determine the resistance of the tungsten filament in a lamp. Now, if we look at this graphically, resistance as a function of temperature, this graph is going to start out somewhat nonlinear, but this is a power equation, and we'll see that the temperature or the resistance increases somewhat exponentially as temperature increases. Now, this graph is showing us temperature in Kelvin, and that is somewhere around 3,000 degrees. Now, believe it or not, the filament of an incandescent bulb is at about 3,000 degrees. But it's not quite that hot to us because of the fact that there's a vacuum existing around the tungsten filament and surrounded, of course, by some glass. But you've got to think about how hot does something have to get to be white hot, and that is about 3,000 degrees. So again, we've looked at resistances, both ohmic resistances, which are fixed or relatively constant, and non-ohmic resistances, resistances that change due to some physical parameter change. And we looked at examples of the thermistor, the light-dependent resistor or photoresistor, and the tungsten filament of an incandescent lamp.